Okay, look at the picture that's shown to you there. Okay, this is the blue curve is described by this function. R of t equals t squared minus t, t squared plus t. Okay, that gives you that blue parabolic type curve. All right, now let's say for the sake of argument here that t stands for time. Then you can figure out your location on the curve at any time. Okay? Like, for instance, let's do this. Let's say that you're walking, okay? And let's say that time is measured in hours. Then you could say, okay, where are we starting our hike? And the answer would be you're starting right here, because that's your location when time is 0. And then you could ask the question, where will we be in 1 hour? And the answer is you'll be right there in 1 hour. And you could say, where will we be in 2 hours? And the answer is you would be right here. Okay? Notice, here, let's put again where we started. Notice the distance we walk in the first hour and compare that to the distance we walk in the second hour. You see, in the second hour we walk a lot further than we do in the first hour, right? Maybe the first hour is uphill and the second hour is downhill. Something like that. Or maybe we just speed up. Okay, you can figure out how fast you're going by just calculating the magnitude of r prime of t. Let's write this down. Okay, your speed at time t equals the magnitude of r prime of t. Okay, so let's calculate how fast we're going in the middle of the first hour. Okay, so I'm going to write speed at half hour. Okay, let's find r prime of t. Okay, so that'll be 2t minus 1, comma, 2t plus 1. So r prime of 1/2 will be the vector 0, comma 2. And so the length, or the magnitude of that vector, is the square root of 0 squared plus 2 squared, which is 2. So our speed is 2. 2 what? Well, I've been saying that time is, in this example I just made up, I said, let's suppose that it's hours. Okay. Let's suppose that distance is in miles. You might expect me to use the variable d for distance, but let's use the variable s. Don't worry about why am I choosing s, okay? Let's just do that. So our speed at a half hour is 2 what? It would be miles per hour. It's distance per time, unit of distance per unit of time. Okay, so right here in the middle of the first hour, we're going 2 miles per hour. Let's calculate how fast we're going at the middle of the second hour. So that would be speed at 1.5 hours. Okay, so r prime of 1.5 will be the vector 2, 4. And so, what's the magnitude of that? The magnitude would be the square root of 2 squared plus 4 squared. So that's the square root of 20, which is approximately 4.5 if I'm going to round off to 1 decimal place. So do you see why we traveled a lot further in the second hour than we did in the first hour? We're going a lot faster. Okay? All right, so that's pretty simple stuff. But now I want to change it a little bit. Now I want to measure my location by distance. Okay, let's get rid of some of this stuff now, and I want to repeat a few questions that I asked a minute ago. So a minute ago I asked these questions. I said, where are we starting? And the answer is there. I said, where will we be after 1 hour? Right here. Where will we be after 2 hours? Right here. Okay, now I want to ask a different question. What if our question is, where will we be in 1 mile? Where will we be in 2 miles? And so on. So in other words, what if I want to break up the path by miles instead of hours? So in other words, by distance instead of time. Okay, then it would look like this. Then it would look like that, you see. And now I would say we're starting here in 1 mile, not 1 hour, but in 1 mile we'll be here. In 2 miles we'll be here. In 3 miles we'll be here, and so on. Okay? That is called parameterized by arc length. Some people say reparameterized by arc length, because the curve was originally broken up by time, or whatever t stands for, and now we've changed it so that's broken up in a different way. It's broken up by distance along the path. So that's arc length. It's broken up by units of arc length. Okay? Now, I want to show you how to do that. It's a pretty easy process to change from the original parameterization to the arc length parameterization. It's pretty simple. Okay? Here are the steps that you follow. Okay, number 1. You calculate S as a function of t. And you already know how to do this, believe it or not, because what is s? S is distance, right? Distance along the path. So in other words, s is just the arc length from 0 to t. And you already know that. It is the integral of, you have to think back a couple of weeks because we had spring break and stuff, so it's been a little bit of time, but how do we calculate arc length? It's the integral of the magnitude of r prime from 0 to t, and because I'm using t up here, I cannot use it as my variable of integration, and so we used a u there instead, and we integrate with respect to u. Okay, so in other words, you're just calculating the arc length from 0 to t. Okay, and we call that arc length s, and because it will be a function of t, I wrote s of t. Okay, that's the step 1. Step 2. Solve for t in terms, let me say it like this, as a function of s. Okay? And then step 3, replace t in r of t with the expression for t in terms of s. Now I want to practice this with you, but I want to practice one that's not super difficult. The example we looked at so far would be kind of a difficult integral. You see, the only real work you're having to do is here in the first part. Step 1 requires some calculus. Step 2 just requires algebra, and step 3 is a simple replacement. So step 1 is the only place where you have to do any calculus. And if we try to do that with this function here, the calculus is quite messy. So I'm going to give us a different one instead. So let's do the vector valued function r of t equals 3t plus, 3t minus 1, comma 4t plus 2. And let's reparameterize that by arc length. Or I could say it this way. Let's find the arc length parameterization. Okay? All right, so here's what we do. Step 1, calculate s as a function of t, where s is just the arc length. Okay, so here's what I'm going to do. I'm going to write r prime of u. Let's calculate that. This particular one is really easy, isn't it? Because it's just going to be 3 comma 4, isn't it? So what's the magnitude of that? It's the square root of 3 squared plus 4 squared, which equals 5. So we write S of t equals the integral of 5 du from 0 to t. So that equals 5u from 0 to t, which equals 5t. So S equals 5t. Okay, that's important. S of t, well, let's not even write the of t this time. Let's just write S equals 5t. Okay, S equals 5t. So step 2, solve that for t, and we get t equals 1/5 x. S. Step 3, take your original function and replace t with 1/5 s. And what will we get? We will get 3/5 s minus 1, comma, 4/5 s plus 2. And I would write R of S. And there is our arc length parameterization for the same function that was up here. I want to make that clear, that if you graph those two, it'll be the exact same curve. It's just that the green one would be broken up by time or whatever t stands for, but usually it's time. And the yellow one would be the exact same curve, except it would be broken up in units of arc length. That's all. Okay. Let's do one more for extra practice. Okay, so this time let's take the vector valued function R of t equals 4t squared plus 2, comma, 3t squared. Okay, so what would be R prime of u? Think about it. It would be 8u, comma, 6u, right? That should be pretty easy. We're just doing derivatives and replacing the variable t with the variable u. So the magnitude of R prime of u would be the square root of 64u squared plus 36u squared. And what's that going to give us? It's going to be 10u. So we integrate 10u du from 0 to t. What's that going to give you? Won't that be 5/2 u squared from 0 to t, right? Which is equal to 5/2 t squared. So S equals 5/2 t squared. That means that t equals the square root of 2/5 s. So our arc length parameterization will be R of S equals, and I replace the t's with square root of 2/5 s. So we'll have 4, whoops, I didn't mean to put a square root symbol. I meant to put vector symbols. So we'll have 4 times square root of 2/5 s squared plus 2, comma, 3 times square root of 2/5 s squared. What is that? That's 8/5 s squared plus 2, comma, 6/5 s squared. Okay, now that's r of s. So now we technically have two different functions here. I'll highlight in green the one we were given. I'll highlight, this time we'll use blue instead of yellow. Highlight our new function that's technically two different functions, but they have the exact same graph. Okay? It's just that this graph is broken up by units of time, and you could calculate a location on the graph at any time. And this one is broken up by arc length, and you can calculate any location along the graph based upon how far you've traveled. Not how much time you've traveled, but how far you've traveled. Okay? From wherever your starting point is. And that's very useful if you think about it. If you were going on a road trip, one possibility is this. You can say, we're going to drive for 9 hours, so let's calculate where we're going to end up after 9 hours. So in that case, you would want to take the map of your journey and break it up into hours and see where you will be after 9 hours. Or you might say to yourself, well, we have enough gas to drive 500 miles, so let's calculate where we will be in 500 miles. In that case, you would want to take the same path, but instead of breaking it up into units of hours, you would want to break it up into units of distance traveled. They're both useful. It just depends on what is the situation you're working in. Okay, that's it for today.